11-2, or I'll do 11-1 of course. And here we go. We're going to take a look now at, what happens if you have two different sets of data that you want to compare one to the other. How do you do that? Well, this is how. We're going to learn how to do that. So one just kind of gives us, it states the hypothesis. We'll have to do that later ourselves, but at this point it states the hypothesis and whatnot and gives us this set of data, or this problem. It says a sample of 40 observations is selected from one population with a population standard deviation of 5. The sample mean is 102. A sample of 50 observations is selected from a second population with a population standard deviation of 6. The sample mean is 99. So we've got two separate populations, right? Conduct the following test of hypothesis using the 0.04 significance level. 0.04 significance level. Okay, here we go. So they give us the hypothesis is that mu1, or basically the mean of 1, is equal to the mean of 2, or that they are unequal. Now because we have the equal and unequal, we know that then for question A, is this a one-tailed or two-tailed test? Gosh, I'm nice here because this one's just almost like a giveaway, but I give you credit if you get it correct. So it's a two-tailed test then, right? Because it's got the equal and unequal. State the decision rule. Well, we got to find our test Z, I guess, if you want to call it that. And we do that, and I don't have it written in here, but our significance level according to this problem is 0.04, right? 0.04. I'm going to put that over here. 0.04 significance. We'll just kind of do that, right? So we got to look that up, and there are a couple ways, I guess you can do this. When it's a two-tailed test, then we've got to, and we're using a z value, which we are in this case, versus a t value. Then we have to take that, and I guess you could say, well, I'll take 0.04 from 1 minus 0.04, that would give me 0.96, and half of that would be 0.48, or you could take your 0.04 and divide that in half, which would be 0.02, and subtract that from 0.5, kind of the midway on our z table, or z area under the z curve. Okay, so then let's get our data. Okay, and you might want to write this out instead of trying to find these symbols. If I remember right, it took me forever to find those symbols and get that looking nice, but I wanted it to look nice for you guys. Okay, so anyhow, you get the mean of 1, right, is 102. The n of 1 is 40, and the standard deviation of 1 is 5. Okay, n being the sample size and the standard deviation being 5. Then you've got the mean of 2 is 99, the sample size of 2 is 50, and the standard deviation of 2 is 6. Okay, and we end up, of course, and they break this down, but if we want to figure out what the variance is, and we can do that because our formula gets a little bit gnarly here. Okay, and this doesn't show up as good as it should be. I advise you to take a look in your book. It shows up better. I don't know if I just couldn't find a good one to copy and put in here, but if you look on middle of page 351, your variance, which is standard deviation squared, right, is equal to the standard deviation, okay, of 1 divided by the sample size of 1 plus the standard deviation of 2 divided by the sample size of 2. Okay, so standard deviation, or the variance. I think I wrote that out wrong, or else maybe they have that. Because it's the, well, hang on a second here. I'm going to pause for a second. Sorry, I was daydreaming. That's right. So it's the standard deviation squared, or the variance of 1. I probably said it wrong. The variance of 1 divided by the number, the sample. I'll get this yet. You guys just hang on. The sample size of 1 and the variance of 2 divided by the sample size of 2. So our variance, they give us a standard deviation, but our variance then is just the standard deviation squared, right? So for this one here, we would have 5 squared, or 25, divided by 40, right? Our n sub 1. Okay, and for this one here, then we would have 6 squared, or 36, divided by 50 in that case, right? So we would have, and I'll just kind of do that. So 25 there, and we would divide it by 40, and really then that's going to be plus, and this would be 36 divided by 50. Okay, and so we'll just say this is equal to this divided by this. Copy, and I'll paste that there. Okay, and then this is plus that, right? So I've got those two, and this is equal to this plus this, and if you add those up, 1.345. Okay, so that's my variance, right, of my the two different samples basically put together. Okay, so now I want to calculate the actual z value, the calculated z value, to compare it to my test z value, right? And so I've got the mean of 1 minus the mean of 2. Let's just do that part. Okay, the mean of 1 is 102 minus the mean of 2 is 99. I'm going to do that one in my head, but we probably should do it this way. The mean of 1 minus the mean of 2, so I get 3. Okay, and then that's divided by the square root, and this is the variance, right? This is just this formula here. So it's divided by the square root, or the standard deviation, right, of these down here. So I can just take the square root of my variance. So delete, I'm going to go, this is a square root, okay, this number, okay, boom, okay. And then to finish that, it's my mean, the difference in my means divided by the divided by the standard deviation of those, okay. And so simply equal to 3. I got those kind of upside down, right? I should have had that one there and this one down below, but I hope you guys are following along. So 3 divided by that, and I end up with 2.5867. Okay, and the decision rule, which I stated up here and I didn't talk a lot about, but it was reject if the null is greater than, and we always do that, you know, greater than 2.05, or z is less than a minus 2.05. And when we have a two-tailed test, that's what we're doing. Remember, we're really interested then in we're going to reject the null if our calculated z is either out here in this area, or, you know, out here in this area. Okay, so what do we end up with here? We end up 2.58. Well, it is greater than 2.05, so we reject the null. So to heck with the null, we're going to go with the alternate hypothesis, is that these two samples, you know, with their deviations and with their means, the means is actually what we're comparing here. Okay, so these two means are actually different. Okay, and we have to find a p-value. And remember, we find the p-value by looking at our z value, and I got the little z chart here, right? And what we calculated was 2.59, let's say. Okay, so I come here, 2.59 is way out here, okay, but it's 4.4952, 0.4952, okay, and remember that's that's based on, you know, the midpoint here, and so 0.4952, if I come way out here, 49, wow. Keep going. Ooh. Oh shoot, I had it. 0.4952. Okay, corresponds to a z of 2.59, but I've got kind of two areas, okay, and so what I actually have to do is take that times 2, right? And so I would say that, let's just say this is equal to 0.5 minus 0.4952, right? It's 0.0048, and I take that times 2 because I've got a two-tailed test, right? So my p-value is still just tremendously small, right? 0.0096. So less than 1% chance, right, that these are equal, okay? That these would be considered equal. So there you have it. Again, the formulas get they get bigger, okay? I wouldn't call this any more gnarly. Actually, the math in this is pretty simple. It's just a matter of keeping it together and organized, and then it comes along fairly easily. So good luck.